Binet is different than the standard deviation of the Wechslers. Now, what I had students do in class is I had them standardize the values on each of the 2IQ scale curves. Basically, redraw these values on the curves as on my axis, but changing them to the z-scores. And I had them do that on both curves, and then generalize their findings. What students should notice is the fact that their z-scores, or their standardized values along the axis of both curves, ended up being equal. And the reason that that's so important is because it shows the fact that standardization of different measurements essentially neutralize the units. It basically is what allows us to use one table in order to find probability for all normal curves. So once again, if you don't have Table A out already, I would suggest you get it out now. Now a couple things, little tips and tricks on how to display or identify the distribution of a data set is you typically want to identify the shape, the center, and the spread. So I want to identify it as being approximately normal with a certain mean and standard deviation, for example. Now this notation right here in red basically is just a shortcut to identify those three values, and you can use this as kind of a shorthand method. So the capital N represents it being a normal distribution, the 0 would be my mean, and the 1 would be my standard deviation. Basically it's in this format of the blue down here. All right, now if you ever forget which one comes first, the mean or the standard deviation, a little trick to remember it is think alphabetical order. The mean comes before the standard deviation, just like M comes before S in the alphabet. Now a sample question that I see a lot of times on AP tests is to identify the distribution of the given data. For example, my response for this case could be that the distribution of the given data is normal with a mean of 15 and a standard deviation of 2. This shorthand notation just allows me to say that much quicker without having to write out so much. Please know that if you decide to write it out in words rather than in this notation, that's perfectly acceptable as well. Alright, so I'm going to show you how to actually use this Table A in your textbook. Now at the top of your Table A, you should notice that there's a picture very similar to this, and it identifies the fact that if you find any z-score on a normal distribution and look it up on Table A, the table will give areas to the left, and always to the left. Now remember, the area under any density curve should be 1. So if I can find the area to the left under this curve, I could use 1 minus that area to find the area on the right-hand side. For example, if this green area I looked up and I found was 20%, I would know the blue area has to be 80%. This is what your table should look like, and for example, if I want to find the proportion or the probability of getting an observation with a z-score less than 2.22, I'm going to go along the vertical axis of my z-scores, and I'm going to find 2.2, and I'm going to scroll all the way over until I find the missing, second decimal place of 0.02. And that'll tell me the probability of getting a value less than that z-score. So this was a problem that students tried in class. It said find the proportion of observations from the standard normal distribution that are greater than a negative 2.15. Now the trick with this problem is notice that the problem asks for the probability of being greater than. Now remember, the table only gives areas to the left. So if I want to find the probability of being greater than, I'm going to have to do 1 minus the area to the left. So here's my table, and I look up a negative 2.15, and I get an area of 0.0158. A common mistake is for students to report that as their final probability. But once again, that is the area to the left or less than my z-score, and I want the area greater than, which is why I did 1 minus the probability of 0.0158 to get my final probability. The proportion of the observations that are greater than a z of negative 2.15 is approximately 98.42%. You can list your percent either in decimal form or percentage form, just don't forget the percent symbol if you decide to do so. So common mistake is to look up the z-value and report the probability that corresponds to it regardless of whether the problem asks for the area to the left or to the right. So kind of a tip in order to help avoid this mistake is to draw a distribution. Sketch your normal curve, mark the z-value, and shade the area of interest. Make sure your answer is reasonable in the context of the problem. So for example, if I'm looking at the IQ problem from previously, I have my mean of 100 and my standard deviation of 16. Now if I want to find the probability of being higher than 109, a score of 109, I'm going to identify where that falls on my distribution, falls right about here. And since I want the probability of being greater than 109, that's why I'm shading greater than. If I wanted to the left, I would have shaded to the left. Notice when I look up the z-score for 109, it's going to give me the area to the left. A lot of times I'll identify that by drawing an arrow to the left and labeling it with the probability. And then that helps me see that I need to do 1 minus that probability. Now to fully do a normal distribution calculation, there's several things that you need to include, and I'll show you an example of this shortly. First of all, you need to state the problem in terms of the observed variable x and identify the distribution. For example, let x be the score on the exam. Step 2, standardize and draw a picture. Standardize your x value, basically find the z-score, and then draw your picture and shade your area of interest. Step 3 doesn't really have any work to show. It's purely the act of using the table to find the probability. And the most important step of all is step 4, write your conclusion in context of the problem. Here's an example. The level of cholesterol in the blood is important because high cholesterol levels may increase the risk of heart disease. The distribution of blood cholesterol levels in a large population of people of the same age and sex is roughly normal. For 14-year-old boys, the mean is 170 milligrams of cholesterol per deciliter of blood, and the standard deviation is 30 milligrams per deciliter. Levels above 240 milligrams per deciliter may require medical attention. So the question that we are told to investigate is, what percent of 14-year-old boys have more than 240 milligrams per deciliter of cholesterol? So I'm going to start by identifying what I'm measuring in terms of x, the level of cholesterol in the blood. And I want to know what proportion have values greater than 240. The only other thing I need to identify before I draw my distribution is I need to identify its shape, center, and spread. It's normal with a mean of 170 and a standard deviation of 30. Step 2 is to standardize and draw my picture. So you'll see that I plugged in my observed value of 240 minus the mean over the standard deviation, and that gave me a z-score of 2.33. Now, sure enough, if I identify a z-score of 2.33, it falls above the mean, and I shade above because I want to find the probability of being greater than 240. Step 3 isn't really anything for me to show, but it's more the fact of me using the table. The table is going to give me the area to the left, which is 0.9901, which means the area to the right is about 1%. So I'm going to write my conclusion in context now. There's only about a 1% chance of picking a 14-year-old boy that has dangerously high cholesterol. Now I want to clarify a couple quick things. If I ask for the probability of selecting a boy with cholesterol above 240 versus selecting a boy with cholesterol of 240 or more, those are technically slightly different things. In fact, there is an area directly above the value of 240 that would not be included in this probability, but would be in this probability. Now, the thing that's nice about statistics is that it's all about practical application. So the fact that there's practically no area above the under the curve, exactly above 240, means that the probability is going to change extremely slightly if you include 240 versus if you don't. Now once again, since it's practical application and those probabilities are going to be so similar, we treat them the same in statistics. So let's try one more example. What percent of 14-year-old boys have blood cholesterol between 170 and 240? So notice, I have a normal distribution of 170, a standard deviation of 30, I'm measuring the level of cholesterol, and I want to know the probability that it's between 170 and 240. So now I need to standardize my value and draw my picture. So I've drawn my picture, identifying 170 as my center and 240 as falling above it. Now, since 170 is my mean, I know the area to the left is just simply 50%. Now, if I look up the z-score for 240, which I found previously of 2.33, that's going to tell me the area below 240 is 0.9901. Now, if I simply want the shaded area between the two values, I can use subtraction. I can do 0.9901, take away the unshaded part that I don't want of 0.5, and that gives me 0.4901. So here's my context. Therefore, I can conclude that there is approximately a 49.01% chance of randomly selecting a 14-year-old boy who has a blood cholesterol between 170 and 240 milligrams per deciliter. One thing to note is notice I have my units. Little challenge here. It says find the probability of getting a z-score less than a negative 4.3. So go ahead and take a look at your table. What is the smallest z-score that your table shows? You'll notice negative 4.3 is not on the table. So we're going to have to use some basic logic in order to answer this question, or at least estimate this question. The smallest z-score on the table is a negative 3.49. And notice when you look up that z-score, it has a probability of 0.0002 to the left of it. Now think logically. If you're even further to the left, how much area is going to be under that z-score? Well, the answer is approximately 0. Technically, yes, there is area to the left of a negative 4.3 z-score, but it is so tiny at that point that we can state it as being approximately 0. Now, a similar case, the probability of getting a z-score above a negative 5.1, once again, that's not on the table. It's too far away from the mean. So I'm going to sketch it. Negative 5.1 falls extremely far to the left. So there's tiny bit of area below it. But since there's such a small area below it, it means that practically all the area is in fact above it, meaning the probability is approximately 100%. So don't panic if you do a problem and you get a z-score that's either really far below or really far above. You can use this simple method to estimate the probability. And last but not least, I want to show you the fact that you can use the table in two directions. If you know the z-score, you can look up the probability, and vice versa. If you know a probability or a proportion on a curve, you can look up the z-score that goes with it. So for this problem, it says the scores of the SAT verbal test in recent years follows approximately normal distribution with a mean of 505 and a standard deviation of 110. How high must a student score in order to place in the top 10% of all students taking the exam? Well, remember we have our z-score formula, and in this problem, I'm going to plug in everything that I know currently. I can plug in my standard deviation of 110, I can plug in my mean of 505, but notice I'm trying to solve for the observation. I don't know how high a student must score in order to fall in the top 10%. But I do know if there's 10% in the top of the distribution, that means I'm looking at them beating 90% of the students. So 10% at the top of the distribution means 90% below the student. So I'm going to go on here and I'm going to look for 90%. Now sure enough, if you look right down here, my probability of 90% falls between these two values, which means its z-score is going to fall between the two z-scores that are listed. So if I move over here, I'm on the line that says 1.2, and it falls between these two values, which is between 0.08 and 0.09. So the best z-score that I can use is probably a 1.285, just as a little bit of a better estimation than choosing one of those options. So I'm going to plug that in for my z-score, and now I'm back to Algebra 1. I can solve for x. If I solve for x, I should get 646.35, which means a student needs to score at least 647 in order to be in the top 10% of all students taking the SAT. I hope this helped in terms of learning how to use Table A, both to find probabilities and working backwards to find observations. Please let me know if you have any questions or concerns, and I'd be happy to get back to you.